What you're about to see is not a feature demo. It's an example of how we design and build complex mobile platforms where identity, security, performance, and scale all matter at the same time. Amalgamate is the system we'll use to walk through those decisions. The challenge we set out to solve was this: how do you build a mobile application that combines authentication, identity verification, voting integrity, media engagement, and monetization without pushing fragile logic to the client or sacrificing performance? Answering that question shaped every architectural decision you'll see in this walkthrough. So instead of starting with screens, we'll start with how we structure systems and enforce rules. User roles and permissions, designing for control, not convenience. One of the first design decisions we make in platforms like this is to avoid binary user states. Users are never just logged in or logged out. In this system, a user can exist in multiple authorization states: authenticated but unverified, partially verified, fully verified, administrative. This matters because in real-world platforms, authentication alone is never enough. We enforce permissions using JWT-based authentication, backend verification flags, and action-level authorization checks on every request. The client never decides what a user can do. It only requests actions. This is a pattern we consistently apply when building systems that must remain secure under manipulation, concurrency, and scale. With that foundation in place, we can safely move into onboarding. Identity, verification, and authorization layer, engineering trust, not just login. In most applications, identity ends at authentication. A user logs in, gets a token, and the system assumes trust. That approach works for low-risk products. It breaks immediately in platforms where actions have real consequences. So one of the earliest decisions we made here was to treat identity as a continuous state, not a one-time event. This section is less about screens and more about how we design systems that cannot afford to be wrong. Identity as a state machine, not a Boolean. Instead of asking, "Is this user logged in?" the system constantly asks, "What level of identity has this user proven? What actions are allowed at this exact moment? What happens if that status changes?" From an engineering perspective, this turns identity into a state machine. A user moves through states such as registered but unverified, contact information verified, biometric verified, government ID verified, fully authorized for restricted actions. Each state transition is explicit, stored server-side, auditable. Nothing is inferred from the client. This allows us to gate actions progressively rather than all at once. Authentication exists to answer a single question: who is making this request? It does not answer whether the user can vote, whether they can comment, whether they can engage with restricted content. That separation is deliberate. JWT tokens are used for authentication, but authorization is evaluated separately on every protected action. This means a valid token does not guarantee permission. Every request is checked against the current verification state. Permissions can change without forcing logout. This is critical for systems where identity can be upgraded, downgraded, or revoked. Email and phone OTP verification exist for one core reason: to prove control over the identity channel before trust is extended. From a backend perspective, OTPs are short-lived, single-use, rate-limited, and tied to a specific intent. This prevents disposable account creation, automated abuse, and replay attacks. Only after OTP validation does the system allow account creation to proceed. This establishes a clean trust baseline before any credentials are stored. Password creation is intentionally strict, not because users enjoy complexity, but because credential compromise is still one of the most common actor vectors. Password requirements are enforced server-side, validated before persistence, and independent of client behavior. Weak passwords are rejected even if the UI is modified or bypassed. This reflects a broader principle we follow. Security rules are never trusted to the front end. Google OAuth is supported for convenience, but it does not bypass internal controls. OAuth tokens are exchanged for backend issued JWTs, mapped to internal user records, and subject to the same authorization rules as all other users. From that point forward, OAuth users are indistinguishable from other users in terms of permissions. This avoids the common mistake of treating OAuth users as inherently trusted. Identity completion as an authorization gate. After authentication, users can enter the app, but they cannot act. This is where identity verification becomes operational, not cosmetic. The system requires users to complete profile details, face registration, government ID submission. Each step updates backend verification flags. Nothing is unlocked until the backend confirms the required state. This prevents UI-only gating, client-side bypasses, partial verification exploits. Face registration. Face registration is one of the most technically sensitive parts of the system. The challenge isn't capturing an image, it's ensuring a real person is present. The system actively detects a face, does not start capture until detection succeeds, rejects frames without sufficient confidence. This reduces background captures, accidental scans. The result is biometric data that can be trusted as part of an authorization decision. Government ID verification, human in the loop by design. Government ID verification is intentionally asynchronous. Why? Because fully automated verification introduces unacceptable false positives and negatives. Instead, IDs are uploaded securely. Automated document analysis assists the process. Final approval happens through admin workflows. This introduces a human-in-the-loop checkpoint where it matters most. Once approved, back-end authorization flags are updated. Restricted actions become available immediately. No client updates are required. This design allows trust to be extended deliberately, not automatically. Authorization at the moment of action. One of the most important principles in this system is authorization is checked at the moment of action, not at screen load. This means a user who loads a screen while authorized but loses authorization cannot act. A user who becomes verified mid-session gains access without re-login. Stale client assumptions never grant access. Every sensitive operation, voting, media, moderation, revalidates token authenticity, verification state, action eligibility. This eliminates an entire class of race conditions and bypass attempts. Failure states are explicit and safe. Identity systems fail in the real world, so we design for failure deliberately. If face verification is incomplete, ID approval is pending, tokens expire mid-flow, authorization is revoked, the backend rejects the request clearly. No partial actions, no silent failures, no ambiguous states. The user experience reflects reality, not optimism. Why this layer matters. This entire identity and authorization layer exists to answer one question. Can we trust this action right now? Everything else in the platform, voting, media, moderation, depends on that answer being correct. This section demonstrates how we design identity systems beyond login, enforce authorization without UI shortcuts, combine automation with human oversight, and build platforms where trust scales with usage. And this approach is transferable. It's the same mindset we apply when building any system where correctness, accountability, and security are non-negotiable. After registering their face, users can log in using it, enabling passwordless authentication that improves security, reduces login time, and enhances overall user experience. Performance and scale decisions, designing for real usage, not demos. Once identity, voting, and media workflows are defined, the next challenge is performance. not in ideal conditions, but under real-world constraints. Mobile platforms don't fail because features are missing. They fail because systems slow down, memory spikes, or network conditions degrade. So performance and scalability were not treated as optimization steps at the end. They were treated as core architectural requirements from the start. Designing for mobile constraints first. The first constraint we design around is the mobile device itself. Mobile apps operate with limited memory, variable network quality, background execution limits, and battery constraints. Because of that, the app is designed to be lightweight on the client, predictable in memory usage, and defensive against unstable networks. This is why the front end is intentionally stateless wherever possible, and why critical decisions never rely on client-held assumptions. Incremental data loading instead of bulk fetching. One of the earliest decisions was to avoid loading large datasets up front. In applications with polls, videos, and events, it's tempting to fetch everything and paginate locally. That approach breaks quickly at scale. Instead, this system follows an on-demand loading model. Only the data required for the current viewport is fetched. Additional data is requested as the user scrolls. Requests are idempotent and resumable. This reduces memory pressure, initial load time, network waste, and more importantly, it allows the system to scale without changing the client architecture as data grows. Efficient list rendering at scale. Rendering large lists is one of the most common performance bottlenecks in mobile apps. To address this, the front end uses high-performance list virtualization rather than default rendering strategies. This ensures only visible items are mounted in memory, off-screen components are recycled, and scroll performance remains smooth even with large datasets. This becomes especially important in poll feeds, short video lists, and event listings. Without this approach, performance degrades linearly as content grows. Video playback and media optimization. Short-form video introduces an entirely different performance profile. Video is bandwidth-heavy, memory-intensive, and sensitive to frame drops and latency. To handle this, video playback is optimized with controlled buffering strategies, caching of frequently accessed media, and network-aware loading behavior. Videos are never treated as just another API response. They're isolated from transactional logic so that media delivery does not block user interactions. Playback remains smooth even when background requests occur. Voting and engagement actions remain responsive. This separation is intentional and critical for scale. Backend performance, separating speed from integrity. On the backend, performance is treated differently depending on the type of operation. Not all requests are equal. Read-heavy operations, such as loading polls or video metadata, are optimized using caching strategies. Write-heavy, integrity-sensitive operations, such as voting, are never cached. Instead, votes are written atomically, constraints are enforced at the database level, and consistency is prioritized over raw speed. This separation ensures that the system remains fast where it can and correct where it must be. Redis caching with clear boundaries. Caching is used deliberately, not aggressively. Redis is introduced only where data is frequently requested, staleness is acceptable, and cache invalidation is predictable. Examples include poll metadata, category listings, non-sensitive configuration data. Sensitive operations like voting, identity verification, and authorization checks always hit authoritative data sources. This prevents cache-related inconsistencies that often appear at scale. Network resilience and failure handling. Performance is not just about speed, it's also about behavior under failure. The system is designed to handle network interruptions, partial responses, timeouts, and duplicate requests. Client-side requests are structured so that failed requests can be retried safely, duplicate submissions do not result in duplicate writes, and the UI reflects real back-end state, not assumptions. This makes the platform resilient in real-world usage where connectivity is unreliable. Why these decisions matter. None of these decisions are visible as features, but they directly impact app stability, user trust, scalability, and long-term maintainability. This section demonstrates how we approach performance as a system-wide concern, not a UI polish step. We design mobile platforms that remain responsive as data grows, behave predictably under load, fail safely instead of silently, and scale without rewrites. And this is the difference between building an app that works in testing and one that survives production.
Home and polling, implementing high-integrity workflows. With identity enforced, we move into polling, the most integrity-sensitive feature. Polls are categorized dynamically: location-based relevance, recency, expiry, verification requirements. Each poll carries full context: creator, description, optional media, and engagement actions. But the critical work happens when a vote is submitted. Every vote revalidates user identity, enforces one vote per user at the database level, is written atomically, and remains auditable. This is not UI-driven logic. It's enforced at the backend and data layer, which is how we design systems where correctness matters more than speed alone. To maintain performance, data is loaded incrementally. Large data sets are paginated and rendered efficiently using optimized list handling on the front end. This balance between integrity and responsiveness is intentional. Short videos, integrating media without breaking rules. Short-form video introduces a different type of complexity. Media is asynchronous, voting is strict. So instead of loosely attaching ballots to videos, we link them atomically on the backend. When a user watches a video, playback is optimized and cached. Engagement actions are available. Ballots appear only after playback completes. At the moment of voting, eligibility is rechecked, expired or invalid ballots are rejected, and verification rules are enforced again. This pattern, validate at the moment of action, not at load time, is something we apply consistently in interactive systems. Profile and account controls, designing for ownership and safety. As users engage more deeply, control becomes important. The profile section centralizes profile updates, password changes, voting history, saved ballots, referral earnings, account deactivation and deletion. Sensitive actions are always revalidated server-side. Account deactivation requires admin intervention to reverse. Account deletion results in permanent data removal, not soft hiding. These decisions reflect how we design systems for real users, real consequences, and real accountability. Admin panel, enforcing integrity at scale. Everything we've covered so far works at the individual level, but real platforms succeed or fail at scale. The admin panel is where we demonstrate how we design operational control systems, not just user-facing features. Administrators gain visibility into voting patterns, category-level engagement, demographic participation, platform usage trends. This data is presented through dashboards and global map views, not for presentation, but for fast operational decisions. Admins also directly control ballot creation and lifecycle, category management, user verification states, government ID approvals, content moderation, and event creation and publishing. These actions are not cosmetic. Every admin decision updates backend state, modifies authorization rules, and immediately affects user permissions and content visibility. This is how we ensure that trust does not degrade as the platform grows. It's also how we design admin systems that remain usable under real operational pressure. Edge cases: how the system behaves under stress. No real system avoids edge cases, so we design for them. When tokens expire, verification is incomplete, users attempt restricted actions, or data becomes stale, the backend fails safely.
Requests are rejected explicitly. No partial writes occur. No silent failures exist. This predictability is critical in platforms where correctness matters more than optimistic behavior. Closing. What this actually demonstrates. Up to this point, we've walked through a complete platform. But the purpose of this walkthrough was never to promote a single application. It was to demonstrate how we approach building complex, production-grade mobile systems. Amalgamate is simply the environment where those decisions are visible. What this platform shows is how we think when the requirements are real. When identity cannot be optional, when actions must be auditable, when performance and security must coexist, when client-side shortcuts are not acceptable. Every workflow you've seen, from sign-up to verification to voting to moderation, reflects a deliberate engineering mindset. We design systems where the backend is the source of truth, authorization is enforced, not implied. Media, payments, and civic actions operate under the same rule engine. Failure states are predictable and safe. This is the level of thinking required when building applications for real users, real data, and real consequences. And none of that happens by accident. It comes from the technology choices we make, and more importantly, how we use them together. So, to close this walkthrough, it's worth looking directly at the technical foundation that made all of this possible.
Technical stack. How the architecture supports the decisions. Everything you've seen in this walkthrough maps directly to the technology stack behind it. The stack wasn't chosen for trendiness, it was chosen to support scale, maintainability, and enforcement of rules at every layer. Mobile frontend. React Native, iOS, and Android. The mobile application is built using React Native 0.74.5 with TypeScript, allowing us to maintain a single shared codebase across iOS and Android without sacrificing performance. This is what enables consistent behavior across platforms, faster iteration without duplicated logic, strong type safety across complex user flows. The front end follows a modular, scalable architecture where features are isolated rather than tightly coupled. State management is handled using Redux Toolkit, which allows predictable state transitions, clear separation between UI state and server data, easier debugging in complex workflows like voting and verification. All API communication is secured using Axios with JWT-based authentication, ensuring tokens are attached consistently, expired sessions are handled safely, and authorization failures are never ignored. To support scale and performance, FlashList is used for rendering large poll and video datasets. Video playback is optimized with caching and smooth rendering. Lists are loaded incrementally, never all at once. The app also integrates Firebase authentication, analytics, Crashlytics, and notifications for observability and reliability, Google Places for location-aware experiences, theme support, navigation stacks, and reusable UI components ensure that complexity remains manageable as features grow. Backend, .NET 8 and Azure ecosystem. All critical logic lives on the backend. The server is built using ASP.NET Core on .NET 8, following clean architecture principles, so that business rules remain independent of delivery mechanisms, security logic is centralized, and features can evolve without breaking existing workflows. The backend acts as the single source of truth for authentication, authorization, voting integrity, verification state, and content eligibility. Data is stored in Microsoft SQL Server hosted on Azure, where voting operations are enforced atomically, constraints prevent duplicate or invalid actions, and auditability is preserved. To handle scale and performance, Redis cache is used for read-heavy operations. Frequently accessed data avoids unnecessary database hits.
media assets such as videos and documents are stored in Azure Blob Storage, separating heavy media delivery from transactional logic. Identity, AI services, and tooling. Identity verification is supported using Azure AI and Azure OpenAI services for face recognition and automated document scanning for government ID verification. These services integrate directly into backend workflows, ensuring verification results cannot be spoofed at the client, authorization flags update only after validated results, Swagger UI is used to document and test APIs, and clear contracts exist between front-end and back-end teams. The value of this walkthrough is not the app itself. The value is in showing how we design mobile systems that scale, enforce trust at the backend, integrate complex services cleanly, and build React Native and .NET platforms that behave predictably under real-world conditions. Amalgamate serves as a concrete example of how we design systems, make architectural decisions, and execute end-to-end development across mobile and back-end technologies. We appreciate the opportunity to share our work and our thinking. If you're looking to build secure, scalable, production-ready applications, we'd be glad to explore how this same approach can be applied to your next product. Thank you.